A 4-year-old boy sets off walking with the other kids. First minute, he looks completely normal. Then he stalls and asks to be carried.
And his blood sugar is 41.
Low. But here's the part that should stop you cold. His urine has no ketones. None.
Low sugar and no ketones. Those two shouldn't happen together.
They shouldn't. And that single contradiction is going to walk us all the way back to one broken gene.
Quick hello. I'm UA. This is the USMLE Reasoning Lab, where we don't memorize answers. We build the logic until the answer has nowhere else to go.
And today the logic is beautiful, honestly. Let's meet him properly. 4 years old, brought in because he tires far too easily. Mom says he starts out fine, then he's done. He wants to be carried.
Any recent illness?
None. He's a cheerful, playful kid. He sat and walked a bit later than his siblings, but his speech and social development are normal.
So this isn't a sick child. This is a child who runs out of fuel.
Hold on to that phrase, runs out of fuel. You just described the whole disease. On exam, strength is mildly down in both arms and both legs. Coordination is intact. No ataxia.
So it's the muscle, not the cerebellum.
Right? And then you listen to his heart and you get two things. A soft systolic murmur and an S3 gallop.
An S3 in a 4-year-old. That's a heart that's dilated and feeling too fast.
That's a failing heart, so put your list together. Weak muscles and a failing heart in a toddler who can't keep walking. Labs. Glucose 41. Creatine kinase 288, so mildly raised. His muscle is being damaged.
And the urine.
No protein, no glucose, no infection. And ketones negative.
Oh, that's the one.
That's the one. Because when sugar drops, ketones are supposed to come up. That's the backup generator. His backup generator never switched on. Then they biopsy the muscle, and the carnitine content is markedly low.
Carnitine. Okay, now we have a name to chase. Let's see the whole question.
Deficient synthesis of which of the following substances best explains this boy's low blood glucose? Your options. A. Acetoacetate. B. Arachidonic acid. C. Glutathione. D. Homocysteine. E. Lactate. F. Palmitate.
Lock in your answer. 5 seconds.
The answer is A. Acetoacetate, a ketone body.
Which matches the urine. No ketones, because he can't make them.
He can't make them, but I don't want you to stop there, because can't make ketones is the last domino, not the first. Let's go find the first one. This disease starts in one place. Not fat, not sugar. One gene. The gene is called SLC22A5, and a gene is just an instruction sheet for building one protein. The protein this one builds is called OCTN2.
And OCTN2 does what?
Here's the key. It is not an enzyme. It doesn't convert anything. It doesn't build anything. It's a doorway, a protein sitting in the cell membrane, whose only job is to carry one specific molecule from outside the cell to inside. And that molecule is carnitine.
So the gene builds a door.
The gene builds a door. It's recessive, so you need both copies broken. One working copy makes enough doors to get by. And when we say broken, there are 3 flavors. And I want you to see them because one of them matters later. 1. The instructions get cut short, so no protein is made at all. 2. The protein gets made, but it folds wrong, never reaches the membrane, and the cell destroys it. 3. The protein does reach the membrane. It's sitting right there in place, but it grips carnitine poorly and cycles slowly.
So in flavor 3, there is a door. It's just a bad door.
A narrow door. And most patients are in that group. Remember that. It's going to explain something that sounds impossible in about 10 minutes.
Okay, but why does one missing door matter this much? Carnitine's a small molecule. Can't it just soak through the membrane?
No. And this is the step almost everyone skips. Carnitine is a zwitterion. It carries a positive charge and a negative charge at the same time. And a cell membrane is essentially grease. Charged molecules do not cross grease. So without a carrier, carnitine doesn't trickle in slowly. It basically doesn't get in at all.
So no door means no entry, full stop.
Full stop. And it's worse than that because OCTN2 isn't just letting carnitine drift through. Inside a muscle cell, carnitine sits at tens of times the concentration of the blood outside.
Uphill.
All uphill. It pumps carnitine against that gradient by riding sodium into the cell. It's a pump, not a hole, which gives you a rule. The more concentrated a store an organ needs, the more completely it depends on that pump. Now the elegant part, the same protein has a job in two different places, so one broken gene fails you twice. Job 1, the kidney. You filter carnitine into your urine all day long, and OCTN2 in the tubule grabs it back before you lose it.
And if it's broken, you just pee your carnitine away.
You pee it away. So urine carnitine goes up while blood carnitine falls. That pairing is the fingerprint of this disease.
So the blood is low and the urine is high. That's backwards from what you'd guess.
And it tells you the leak is renal. Job 2. The same protein on heart and skeletal muscle importing carnitine into the cell. So put it together. The blood has almost nothing in it, and the door into the muscle is narrow. That's a double hit, and that's why the biopsy came back markedly low.
Then why not just eat more or make his own?
Ha! That is exactly the right question. And the answer is my favorite thing about this disease. Roughly 3/4 of your carnitine comes from food. Meat mostly, some dairy. The remaining quarter your body builds from 2 amino acids. Lysine gives the carbon skeleton. Methionine donates the methyl groups.
Does that synthesis need anything special?
It does. It needs vitamin C. 2 of those enzymes are the same family as the prolyl hydroxylase that builds collagen. So vitamin C quietly shows up in 2 completely different diseases.
Okay, so between food and the synthesis, he should have plenty.
And here's the punchline. The last enzyme in that synthesis pathway is called BBOX, and it lives in the liver, the kidney, and the brain. It is not in heart muscle. It is not in skeletal muscle.
Wait, so the heart can't make its own carnitine at all?
Not one molecule. The 2 organs that hold almost all of the body's carnitine and need it the most are pure importers. They have no factory. They only have a door.
And his door is broken, and his kidney is throwing the supply away.
So eating more doesn't rescue him. You can't fill a bucket that leaks through a door that barely opens. Now, why does any of this hurt? Because carnitine is a ferry. A long-chain fatty acid cannot walk into a mitochondrion on its own. So on the outer membrane, an enzyme called CPT-1 hooks the fatty acid onto carnitine. A translocase carries that pair across the inner membrane. And inside, CPT-2 unhooks the fatty acid and releases the carnitine to go back out and fetch another one.
Out, load in, unload, back out.
A ferry running back and forth all day. Take away the carnitine, and you have a dock with no boat. The fat is right there, piled up, and none of it reaches the furnace. And now, every finding in this case falls out in order, ranked by how much each organ depends on burning fat. The heart is first because at rest the heart gets most of its energy from fatty acids. It is the most fat-dependent organ you have.
So it's the first to starve.
Chronically short of ATP. A weak pump can't empty properly, the chamber stretches, and you get a dilated cardiomyopathy. The stretched chamber gives you that S3 gallop, and a stretched valve ring gives you the murmur.
The murmur isn't a separate disease. It's the same broken door.
Same door, then skeletal muscle. And this explains the mother's story exactly. His first minute of walking runs on glycogen, creatine phosphate, and blood glucose. All fine, all available.
And then he's supposed to switch over to fat.
And the switch fails, so he doesn't get gradually tired. He falls off a cliff about a minute in, and meanwhile the fat he can't burn turns into droplets inside the muscle fibers and chews up the membranes. That's the CK of 288. And now the liver, which is where the answer to the question lives. When the liver burns fat, it produces acetyl-CoA. And acetyl-CoA doesn't do one job. It does three. So when it runs short, three things break at the same moment. 1. Acetyl-CoA is the raw material for ketones. No acetyl-CoA from fat, no acetoacetate. That's your answer, and that's why the urine is clean while the sugar is 41. 2. Acetyl-CoA is the activator of pyruvate carboxylase, the first step of gluconeogenesis. Without it, pyruvate can't be pushed toward glucose, so it spills to lactate instead, and the blood sugar sinks even lower. 3. Acetyl-CoA builds N-acetylglutamate, and that molecule is the on switch for CPS1, the first enzyme of the urea cycle. Turn that switch off, and the urea cycle slows down, so ammonia can climb during a crisis.
Hang on. One molecule running short explains no ketones, low sugar, and high ammonia.
One molecule. That's why I love this question. It's not a list of facts. It's one shortage wearing three costumes.
So walk me through the 5 we threw away.
F. Palmitate. And this is the trap the question is actually built on. Palmitate is a fatty acid you build when you have energy to spare. That's fatty acid synthesis, running the opposite direction. His synthesis machinery is untouched.
So the word fatty acid pulls you in, and the direction is wrong.
He can't burn fat. He has no problem making it. E. Lactate. Glycolysis is fine, and lactate actually tends to go up, not down. B. Arachidonic acid. That comes from linoleic acid. It's the eicosanoid line, nothing to do with the ferry. C. Glutathione. Glutamate, cysteine, glycine. That's the antioxidant line. And D. Homocysteine. That's the methionine cycle.
D is sneaky though, isn't it? Methionine turns up in carnitine synthesis.
Ooh, nice catch. Methionine donates the methyl groups, yes. But nothing about this disease stops you from making homocysteine. Sharing an amino acid isn't the same as sharing a defect.
Here's what still bothers me. If fat is piling up because he can't burn it, shouldn't he be heavy? A thick layer of fat?
Ooh. That is the best wrong instinct in this whole topic, and taking it apart teaches you more than the answer did. Fat tissue isn't the broken part. It stores fat, it releases fat, and it does both perfectly well. The break is much further downstream, inside the mitochondria.
So he isn't storing extra.
He isn't storing extra. He can't reach what he already has. He's a child sitting on a full tank he can't open. So he's in chronic energy deficit. And instead of getting fat, he grows poorly and hits his milestones late, which is exactly what Mum described.
Then where does the fat actually pile up?
Inside the cells that can't burn it. Droplets inside the muscle fibers, which is a lipid myopathy on the biopsy, and fat inside the liver cells. It's microscopic. You'd never see it from the outside. The warehouse isn't overfull. The trucks unloaded on the factory floor and jammed the machines.
All right, treatment. We give him carnitine. But hold on. The door is broken. How does swallowing carnitine get it into his heart?
You've just asked the sharpest question in this episode. And there are 4 answers stacked on top of each other. 1. Remember flavor 3 from earlier? Most patients have a narrow door, not a welded one. There's still some transport happening. 2. Mass action. If you push the concentration in the blood far above normal, even a narrow door passes more molecules per minute. You can't widen the door, so you crowd it. 3. And this is the one that really resolves it. It's a threshold, not a warehouse. The amount of carnitine needed to keep that ferry running is far lower than the amount normally kept in storage, so tissue carnitine can stay below normal, and the heart still recovers. You never refill the warehouse. You just keep the conveyor moving.
So the goal isn't normal levels, it's normal flux.
Normal flux? And 4. The kidney still leaks, so this is a leaky bucket. You keep pouring every single day for life. Stop, and the cardiomyopathy can come back. And it genuinely works. Children in heart failure from this have recovered heart function on carnitine. Newborn screening can catch it before any of that happens from a low-free carnitine.
Any downside to taking that much?
2 worth knowing. Stomach upset, which is dose-related, and a fishy body odor. Gut bacteria convert the extra carnitine into trimethylamine, and that comes out in sweat and breath. It's the usual reason a teenager quietly stops taking it. And it's always the L form that's given. Now let me change one thing and watch the answer move. Same failure to burn long-chain fat. But this time carnitine is normal, or even high. And instead of a toddler, you've got a teenager with muscle pain and dark urine after a long run.
Plenty of bolts. So the machinery is broken, not the fuel.
That's CPT-2 deficiency. And here's the part that matters clinically. Giving carnitine does nothing because carnitine was never what was missing.
Oh, so supplementation only helps when the thing you're short of is the thing you're giving.
That's the whole principle. Change it one more way. Low sugar, no ketones again. But the heart is completely fine and carnitine is only slightly low. That's MCAD deficiency, medium chain. And medium chain fats don't need the ferry at all. They walk into the mitochondria on their own.
So the heart tells you the chain length.
The heart tells you the chain length. That's a rule worth writing down. So here's the rule, word for word. Low glucose with no ketones means the fat-burning line is down. Add a cardiomyopathy, a myopathy, and very low carnitine, and you have primary carnitine deficiency. The SLC22A5 gene builds a broken OCTN2 door, so the kidney leaks carnitine, and muscle and heart can't import it, and they cannot make their own. And it's treatable for life with L-carnitine, because the shortage is the fuel, not the machine.
Gene, to door, to ferry, to every single finding.
That's the episode.
If that made fatty acid oxidation finally click, subscribe. We do one of these a day, and they build on each other.
See you in the next one.